Hey, hi, everybody. My name is Jasmine. I'm accompanied by Alondra and Christian, and we worked alongside our faculty supervisor, Dr. Saini. And over these last 4 weeks, we worked on a process to generate pressurized but CO2-free steam via direct contact steam generation process. And in this presentation, we'll be talking about the motivation behind it, our objectives, our approaches that we took, as well as the setups and our observations. And I will be passing it over to Christian to talk about our motivation.
Hello. So our motivation was really in regards to Dr. Saini's patent pending technology, which is to capture carbon dioxide and through use of direct contact steam generation, really produce sodium carbonate in order to thus capture the CO2. So our objective was really to design an open experimental setup that was really analogous to Dr. Saini's technology in order to neutralize the aqueous solution of sodium hydroxide and thus produce sodium carbonate. So with our experimentation, we used a mechanism of direct contact heat transfer along with the implementation of 100% pure CO2. And we put that CO2 into a vortex that was created in the beaker by use of magnetic stirrer with the solution of sodium hydroxide in order to produce the sodium carbonate. And afterwards, we were to use silicone or cyclone separator in order to separate the precipitate from the aqueous solution. So our approach while we were testing this was really to see the efficacy of our design in order to produce the sodium carbonate, as well as how well we could recover it from the aqueous solution. And our most critical components to this was our use of magnetic stirrer placed underneath the beaker of the sodium hydroxide solution. And this was in order to create the vortex, which was really important to this process. And afterwards, we were to use a blowtorch placed on top the vortex in order to simulate the direct contact heat transfer and thus stimulate the steam. And afterwards, we were to use the cyclone separator in order to separate the solids, which is very important in order to have fresh and clean water. And at that point, I'm going to pass it over back to Jasmine.
All right, so we have two schematics here of processes that we focus more so on. This first one here is the one that's similar to Dr. Rao's technology of his hydroflame. And what it does is it converts an aqueous solution, in this case, the sodium hydroxide, into a precipitate, which was our sodium carbonate. And we use steam with the pure CO2 supply in order to convert it into that precipitate using direct contact heat transfer. And our direct contact method was the blowtorch and the cavity created by the magnetic stir. So as you can see here, we had a magnetic stir with our magnet, and then we had a beaker containing the sodium hydroxide, and the magnet would create somewhat of like a vortex, which allowed us to put our blowtorch into the cavity, and then that would evaporate off and create our sodium carbonate. And then here are the pictures of it in real time. So here's our CO2 tank, and it's connected to a steel tubing that goes into our beaker of the sodium carbonate. And then here is it up close, and here is the flame that's being inserted into the cavity. And then on the other side is this schematic here, and this is similar to Dr. Saini's patented process that he has. And this is for the precipitate, which was the sodium carbonate. We have a submersible pump here with a bucket, and in this bucket, it contained fresh water, and we used silicone carbonate or carbide actually, and salt, sand to kind of test our theory of the sodium carbonate. And what it did is it traveled through these pipings here into the cyclone separator. The powder would settle to the bottom, so either the sand or the sodium carbide, and then the fresh water would travel up this white tubing here into this bucket, and then in here we would have our either our sand or sodium carbide and then our fresh water. And then here is it in real time. So here's the cyclone separator, and then here's our 2 buckets, and then our pump and our feeder tank. And I will be passing it over to Alondra to talk about our experimental observations.
Okay, so for our experimental observations, we began with a comparison of our 2 experiment types, the volume of evaporated water in cubic centimeters, the time taken in minutes, and the energy consumed in watt-hours per gram. So our first experiment type was water evaporation via the use of a heating plate, and that is our indirect heat transfer. And to evaporate 30 cc of water, it took 34 minutes, and the energy consumed was 14 watt-hours per gram. And then our second experiment type was water evaporation via the use of a butane blowtorch. And that is our direct contact heat transfer. And to evaporate 30 cc of water for this experiment, it took 20 minutes, and the energy consumed was 3.25 watt-hours per gram. And then we have a plot comparing these 2 experiments. And the blue line represents the water evaporation via the use of a butane blowtorch. And for that one, you can see that the temperature rises much more rapidly in comparison to the water evaporation via the use of a heating plate, which is represented by the red line. So based on these data observations, we can say that the direct contact heat transfer based evaporation of aqueous solutions is much more effective when compared to the traditional or conventional heating place based method. And then in our following that, we have our pictures of where we began with the aqueous sodium hydroxide solution. And then throughout our experimenting, it would become precipitated sodium carbonate, and then finally dried sodium carbonate. And our experiment rested on the mole basis, which was 2 sodium hydroxide plus carbon dioxide, which should yield sodium carbonate plus water. And for a 1000 cc solution, we would start off with 40 grams of sodium hydroxide, and we would expect 53 grams of sodium carbonate. And then for a 400 cc solution, we would start off with 16 grams of sodium hydroxide, and we would expect 21.2 grams of sodium carbonate. And after conducting our direct contact heat transfer approach, we observed that it was successful in precipitating out the sodium carbonate from the aqueous 4% weight sodium hydroxide solution. And it was also effective in capturing almost all of the supplied carbon dioxide and transforming the aqueous phase into steam. Lastly, we conducted various proxy separation experiments where we replaced dust and silicon carbide in place of the sodium carbonate particles, because sodium carbonate is an irritant, and dust and silicon carbide have a similar particle size to the sodium carbonate. And in these proxy separation experiments, we observed that the cyclone separation process resulted in varying recovery, so anywhere from 50 to 80% of the solid particles present in the input aqueous solutions.
And we have 3 main points we want to summarize with all of this. The first one being how we use Dr. Rao's technology and Dr. Saini's processes to create open system experiments so we can use the direct contact steam generation approach. And this allowed us to test its efficacy to achieve specific project objectives, somewhat like this one using direct contact heat, and then this one to use decantation to separate solid particles from aqueous solutions. In this case, it was sand and sodium carbide. And then in this one, it being the sodium hydroxide and pure CO2 to create sodium carbonate. And then the next one will be explained to you by Alondra.
And the other main objective of our project was to utilize the silicon separator to view the decantation process of the input aqueous solutions. And like I previously mentioned, we used dust and silicon carbide to view this decontamination of solid particles from the aqueous phase. And then Christian will go ahead and finish off with the third point.
One thing we could all agree upon is that the emission of carbon dioxide into our atmosphere is really quite detrimental to our environment. And we really are nearing a point of no return for the damage that we may cause this planet. That is why there's a large incentive to find solutions in order for there to be less carbon dioxide emission. And this project really provided us with the optimism, thanks to Dr. Sani's technology, for the future of this industry and for a future which may lead to like no carbon dioxide emissions whatsoever, or greatly less than there are today. And on that point, I'd really like to thank Chevron, the NSME department, and the Aqua Energy Environment Engineering Solutions Company for giving us this opportunity, as well as Dr. Sanis, whose passion for this project and his technology really was the driving force for this project and was greatly inspiring for all of us. And I'd really like to thank my partners as well, who were amazing. So this concludes the presentation, and I hope you have a great day.